Hi there, this is an Algebra 2 video. It is Chapter 6, Section 5, and today we are talking about operations with radical expressions. So up first we have the product property of radicals, and although I didn't write it explicitly on the board, we have to remember that A and B need to be real numbers, and n needs to be any integer that is greater than 1. But if that's the case, then the nth root of a product, a times b, will be equal to the nth root of a times the nth root of b. So you can separate those. So I'm going to show you how that works here in example 1. And it says, simplify the square root of 32 times x to the 8th. So what we can do there is, you'll recall that whatever the index is, in this case the index is 2, right? You want to rewrite everything that's underneath the radical, which is basically called the radicand, into groups where they're all squared. Like, so for example, I know that 32 is 16 times 2, so I'm going to go ahead and start there. But also x to the 8th could be written as x to the 4th squared. Okay, because 4 times 2 is 8. Now also, the reason why I broke this down to 16 times 2 is because I know that 16 is 4 squared. So now I have 4 squared times 2 times x to the 4th squared. Okay, so anything that has the square is going to cancel with the square root. So the 4 is going to come out, and x to the 4th is going to come out. And what's not going to come out is the 2. The 2 is going to stay in there. So that's basically your answer, 4x to the 4th root 2. Now remember that you don't need to put absolute value bars in the x to the 4th because it's an even exponent, so it will always be positive, so you don't need to put the absolute value bars in that case. All right, so in part B, we are going to, by the way, if you want to see like where I'm using the property here, I kind of skipped that step, so I'm sorry. But basically I'm saying square root of 4 squared times square root of 2 times square root of x to the 4th squared. Like that. So this one cancels and you get 4. The square root of x to the 4th squared cancels, you get x to the 4th, and this guy stays in the radicals. That's how you get that. So just in case you were wondering, like, well, where does she use the property? There it is. I'll be more careful in part B to make sure I show you that step when I do it. But the first part is to, now we want to write things into groups of 4. So I want things to the 4th power. So 16 is 2 to the 4th power. Pretty sure of it. Yes, just confirm. So 16 is 2 to the 4th power. And then 24 is 6 times 4, so I'm going to go a to the 6th power and then to the 4th power, because 6 times 4 is 24. But with the b, we don't have anything that's times 4 that will give you 13. But we do have 12. We know that 3 times 4 is 12. So I'm going to put b cubed here to the 4th power. So 3 times 4 is 12. And then you have an extra b. Okay, so 2 to the 4th is the 16. A to the 6th to the 4th is a to the 24th. B to the 3rd to the 4th is b to the 12th. But that times b to the 1 is b to the 13. So it's all in there. And now you can actually take the 4th root of each thing individually. Okay, so these little guys cancel, so you get 2. This little guy cancels, you get a to the 6th. And again, because the a to the 6th is an even exponent, this will always be positive, so you don't have to worry about absolute value bars. And then you're going to have this cancel, and that's going to be b cubed. But in this case, b cubed could potentially be negative, so you want to make sure you put that in absolute value bars. And then this b doesn't come out because it has no 4th power. So 4th root of b. And this would be your final answer for part B. You get 2 a to the 6th times the absolute value of b cubed times the fourth root of b. Alrighty then. Now, if you will try do it yourself numero uno, we will go on to the quotient property of radicals. So again, I want to remind you that a and b have to be real numbers. Because you have division, you don't want b to ever be 0, because then you'd have division by 0, that would be a problem. And of course that the n, the index, needs to be an integer, and it needs to be greater than 1. Alright, if all of that is maintained, then the nth root of the fraction a over b could be separated into the nth root of a divided by the nth root of b, and vice versa. Alright, so here we go. It's important for you to remember also in these cases that it is improper to have a radical on the bottom, so you want to rationalize any denominators, and we will talk about that as we go through the problem. Alrighty then. So, square root. So, because you have different variables here, this is a square root, we want to put them in groups of, we're going to go square root, well, we don't have to write the square root, but square root of x cubed squared, because 3 times 2 is going to give you 6. And on the bottom, you're going to have y cubed squared. That's going to be y to the 6th, but this is y to the 7th, so times y. And then you have that. Okay? So on the top, you're going to have them cancel. You're going to get x cubed. And of course, you should keep that in absolute value bars. And then you're going to have on the bottom, the y cube's going to the y cubed square will cancel, and you'll have just y cubed left, and then square root y. Okay, because this y won't come out. Okay, and that's what I meant when I said earlier that you're going to have to be careful with the issues of, you also want to have absolute values on your y cubed there. But you're going to have issues with the square root of y at the bottom. You should not have any square roots on the bottom. So to get rid of the square root, you have to multiply by another square root y. And so now on the top you have absolute value x cubed root y. And on the bottom you're going to get y, square root of y times the square root of y, which is the square root of y squared. Like that, and they're going to cancel. And you're just going to have y left. So then you're going to have y to the 4th, because you're going to have the y cubed from here, and then this is going to be y, so it's y times y cubed, so y to the 4th. And now you don't need the absolute value bars on the y, because the 4th is going to maintain that it stays positive. Alrighty, so this is now your final answer. And then we'll do something similar with part B. Okay, in part B, we're going to first separate it into the 4th root of 6 over the 4th root of 5x. Now in this case, you don't have any issues with trying to cancel things inside the radicand. The problem here is that you have a square root on the bottom, or you have a radical on the bottom. You can't have that. So it's not as easy as part A, where you can just multiply by root y over root y. The only reason why this works is because the radicand, the index, was a 2. So when the index is a 2, then you only need y squared to cancel with the 2. So that's why I did times y, because y times y is y squared, so we get it to cancel. But in this case, if I multiply by simply the 4th root of 5x, it won't work, because what's going to happen is I'm going to get 5 squared x squared, but the index is a 4, and it still won't cancel. The only way for it to cancel is for it to be 5 to the 4th power. So that's what you have to keep in mind when you're trying to rationalize the denominators here. Okay, is that I need to multiply by 5 to the 3rd power, because 5 to the 3rd power times 5 will be 5 to the 4th power. Okay, I need x to the 3rd power, because x to the third power times x is going to be x to the fourth power. Like this. And I have to do that on the top and on the bottom. 5 cubed x cubed. So I hope that that makes sense how that works. You have to make sure that it has the same exponent as the index, otherwise it won't cancel. So now you get the fourth root of 5 to the fourth and the fourth root of x to the fourth, and they cancel and you just get 5x on the bottom. Okay? Again, you should probably have absolute value bars on the x because of the even power. This is an odd power, so it could be negative, and so you want to make sure that it stays positive. So absolute value of x. And then on the top, you have 5 cubed is 125. And then that times 6 is 750. So let's see if I can squeeze this in here. 750x cubed like that. So you get the fourth root of 750x cubed over 5 times the absolute value of x. Alrighty? So I don't know if they want us to simplify the 750, but I don't think so. That is the final answer. It doesn't simplify any further. Alright, so our answer is right there. Awesome. So now if you will try, if you will try do-it-yourself number 2, then we will go on to multiplication of radicals. And so just want to remind you here that when you simplify radical expressions, there's a couple of things you want to keep in mind. How do you know that when you're fully done simplifying? Is obviously the index n is as small as possible. That's not really hard to do. The radicand, which again is the inside, contains no factors that are nth powers of an integer or a polynomial. So basically it has to be fully factored. No perfect squares should be factors at the bottom. For example, in number 12, if this is a square root, then we know that 4 times 3 is factors of 12, but 4 is a perfect square, so we shouldn't have that, and so on and so forth. Radicand contains no fractions, and of course there can't be any square roots or radicals in the denominator. So in this case we're going to use multiplication, and so the first thing we should be mindful of is that when you have coefficients like this in front, those can be pulled together, and you can actually just take and go 5, that's not going to be a good color, 5 times 3, so I'm taking those two right away and just put them in the front. And since they both have index of 3, we can combine them into the same radical and take 18 times negative 12. And that's negative 216. And then we have a and a squared. That's going to be a cubed. And then b to the fourth and b squared is going to be b to the sixth. Because remember, you have to add exponents when you're multiplying the same basis. So b to the fourth times b squared is b to the fourth plus 2. So that's going to be 6. And now we can actually try to simplify this a lot easier. 5 times 3 is obviously 15. We're going to get a cubed. We're going to get b squared cubed, which is 6. And so those are going to be cubed root, and cubed root of negative 216. All right. Let's see here. It turns out that negative 6 to the third power, let me rewrite this, it looks kind of messy here. Okay, hope you can understand it. So It turns out that negative 216 is negative 6 to the third power, so negative 6 times negative 6 times negative 6 is negative 216. And we had our a cubed and then our b squared cubed because that's going to give us b to the 6. So now that I've broken it all down into 3's, I can now cancel what can be canceled. So I'm going to get negative 6 here. And then they're going to cancel. I'm going to get just times a. And they're going to cancel. I'm going to get b squared. Okay, and then of course I still have the 15. Now be careful here because it's not subtraction, this is multiplication. So 15 times negative 6 is going to give us negative 90 a b squared. Now because this is a cubic index, we don't have to worry about absolute value bars. So the answer is just negative 90 a b squared. Alrighty, so now you can try this do-it-yourself example, and then we'll move on to adding and subtracting radicals. And when you add and subtract radicals, it's important for you to understand that you have to have like radical expressions. It's kind of like saying that you have to have like terms. You know that you can add 2x and 3x to 5x because they're like terms. But you can't, for example, add 2x with 5x squared, because one has x to the 1 power and one has x to the 2nd power. So like terms is kind of like what's happening here with these radical expressions, only it means like radicals. In other words, you can add 5 root 2 with 3 root 2. They're like radicals. They both have the same number inside the little house, and they both have the same index. So that's what it means to be like radical expressions, identical index and radicand. So the little number on the outside of the house has to be the same, and the number inside the house has to be the same. If you do that, then you can add them. So in this case, 5 root 2 plus 3 root 2 would be 8 root 2. And it'd be real simple. The problem is that a lot of times students will look at a problem and assume that it can't be added. But you look at this and you go, okay, that's 98 and that's 32. Okay, I can't add them. Well, the point is for you to first simplify the radical, and then once it's fully reduced and simplified, then you can determine whether or not you can add them. 32, for example, I know is 16 times 2. So the square root of 16 is 4. So the square root of 32 is the same thing as 4 root 2. So I'm going to replace square root 32 with 4 root 2. Okay? And the same thing has to happen with 98. We have to figure out how we can simplify 98. Well, it turns out that 98 is 49 times 2. And the square root of 49 is 7. So the square root of 98 is the same thing as 7 root 2. So I replace the square root of 98 with 7 root 2, and now I'm looking at 7 root 2 minus 2 times 4 root 2. Well, minus 2 times 4 root 2 is 8 root 2. And see, now it's actually possible for me to subtract these radicals because they have like radical expressions. They both have root 2. So 7 minus 8 is negative 1. So the answer is negative root 2. So when you're adding and subtracting radicals, it's important for you to first simplify the radical, so reduce it to as much as you can, and then you can determine whether or not you can add or subtract them. All right? So now we're going to let you try this little guy, and then we'll talk about multiplying binomials. Okay, so we already multiplied before where you had a radical times a radical, but in this case you have a binomial. So this is like a term that has two parts to it, and basically the method for doing this is going to be FOIL, and luckily you guys already know FOIL, first, outer, inner, last. Not sure what happened there. Okay, so we're going to FOIL here, and so just keep track of what you're doing. So I'm going to try to show all my work here to make it easy for you. So first times first means 4 root 3 times 3 root 2. That's F. First times first. 4 root 3 times 3 root 2. Then the outside is going to be minus, because this is a negative 6. Okay, so it's minus 4 root 3 times 6. Okay, that's the O. outside times outside. And the inside is going to be a plus, because they're both positive, so it's going to be 5 root 2 times 3 root 2. That's the inside times inside. And last times last is 5 root 2 times the negative 6, so it's going to be negative. Okay, so we have a first, outer, inner, last. So now what's going to happen is 4 times 3 is going to give us 12, but root 3 times root 2 is root 6. Over here we're going to get 6 times negative 4 is negative 24 root 3. And then here you're going to get 5 times 3 is 15. And then you're going to go root 2 times root 2, which is root 4. But the square root of 4 is just 2. So 15 times 2, or just 30. And then lastly, you're going to get 5 times 6, which is negative 30 root 2. So now if there's anything that's like terms, you can try to add them. But we've got a root 6, we've got a root 3, and a root 2. And all of those are reduced as much as they can go. And we can't combine them. So our final answer, believe it or not, is going to be 12 root 6 minus 24 roots of 3 plus 30 minus 30 roots of 2. This whole long thing is going to be our answer. And it's okay that it's like that long. So then, there you go. Now I want you to try this one. And then we're going to go to our last example, which is dealing with conjugates. So we've done conjugates before, and now we're going to do conjugates for radicals. And so basically conjugates would be something like a root b plus c root d, and then the conjugate would be the same thing, but instead of a plus, a minus. So a root b minus c root d. And we use conjugates when you have binomials at the bottom of a fraction, when you're trying to rationalize it, because you want to get rid of the radical on the bottom. And it's not enough to just multiply by root 5. So we're going to do that here in this example. Use a conjugate to rationalize the denominator and simplify 2 over root 5 minus 1. So if I were to multiply by root 5, which is probably what you're thinking to do, then I would get 2 root 5 over root 5 times root 5, which is root 5 squared, minus root 5. And so here lies the problem, is that this would cancel and you'd get 5, but the root 5 over here didn't cancel. See? You only canceled one of them, but then now another one appeared. This is not enough. So we do not want to simply multiply by root 5. You want to multiply by the conjugate of root 5 minus 1, which would be root 5 plus 1. Now if you do this, you will see right now that it will cancel. So you're going to get 2 root 5, because 2 times root 5 is 2 root 5, and then 2 times 1 is 2. So there's the top. On the bottom, we're going to do our FOIL thing. You remember from before that whenever you have a minus b and a plus b, and you FOIL this little guy, you get a squared minus b squared. So I'm going to get root 5 squared minus b squared, which is 1. Okay, so this time, the root 5 squared still cancels, you get 5, but now you get minus 1 squared, so you get minus 1. So our final answer is 2 root 5 plus 2 over 5 minus 1, which is 4. And so now because you have 2 and 4, you can actually reduce this fraction to root 5 plus 1 over 2, because 2 goes into 2 once, 2 goes into 2 once, 2 goes into 4 twice. So you get a 1 root 5 plus 1 over 2. So this is our final answer for rationalizing with the conjugate. So now I'd like for you to do this do-it-yourself question. And trust me that it's going to require some conjugate rationalization. And once you have completed this example, then you will have completed your notes for this lesson. And I will see you in class. And thanks for watching.